Hello, everyone, and welcome to the Demystifying 400 gig with a sneak peek at 800 gig webinar. We're going to allow just another 30 seconds or so for more people to join. I see they're piling on right now pretty quickly. So if we can just wait just a second here, we'll begin the webinar. Thank you for attending, everyone. People are still joining. We're going to give it just a few more seconds. We've got a good crowd that is coming on. Okay, I think we should go ahead and begin. My name is Sue Selby. I'm Regional and Channel Marketing Manager for North America here at VIAVI. We're going to be talking about 400 gig and fiber characterization testing requirements. Your speaker today is Michael Bangert. He has been with VIAVI over 13 years, and he is Product Line Manager for our Metro Group. So a few housekeeping issues. The webinar is approximately 1 hour. You are all in listen-only mode. The webinar is being recorded. We do have a second webinar, same topic, but that will be held on Friday, March 14th. And we will send the recording to attendees after the webinar when we have it in the correct format. So please put your questions in the question window. I'm not sure if we're going to have time for questions, but we will respond to you in any case if you put your questions into the window. So with that said, welcome, Michael, and we are ready to begin.
All right, thanks, Sue, and welcome, everybody. So just what we'll do in terms of agenda today is I'll start talking about what's new with 400 gig. How did we get from 100 gig to 400 gig? I know 400 gig has been out for several years, but a lot of people are still new to it. A lot of organizations are beginning to adopt it. So we'll talk about some of the new optics and form factors, PAM4 and FEC, and some of the optical interfaces that are available at 400 gig. I'll also talk about ZR plus optics, also known as kind of pluggable coherent optics, and we'll talk about how they differ from traditional transport applications, and I'll share some thoughts for how to test and troubleshoot ZR plus deployments. And finally, we'll start with introducing 800 gig. 800 gig is the next line rate that is about to hit networks. And I'll talk about how to get from 400 gig to 800 gig and give you some thoughts on what to look for there. So that's our agenda today. Thanks everybody for joining, and we'll get started. So what's new with 400 gig? The first thing I want to talk about is just how did we get from 100 gig to 400 gig? I think a lot of folks are familiar in general with 100 gig. It's been kind of workhorse for core networks for a better part of a decade. But now we have 400 gig that's out. Again, it's been out for a few years, but many organizations are just beginning to deploy it, specifically in some transport applications or upgrading central offices to support 400 gig. And there's really two ways that we get to, there are two considerations to get to 400 gig. We've got the math equation here is 100 gig times 2 equals 400 gig. And there's really two elements here. One is new optics. At 100 gig, we had QSFP optics we are really using the same form factor for 400 gig. But we added the DD. And then we added a whole new type of optic called OSFP. Both of these two optics have 8 lanes across their connection from the optic module to the equipment, as opposed to 4. So we basically doubled the total number of electrical interfaces that are going out into the optic from the equipment. The QSFP, the DD stands for double density. which really adds an extra row of pins. So if you look at a traditional QSFP optic, it will be slightly shorter than a QSFP DD because of that second row of pins. So that's one of the times two. The other times two is what we call PAM4. PAM4 is pulse mode modulation for levels. What we're really doing with it is we're sending 2 bits of information every clock cycle instead of 1. So you can see in this little diagram, this is kind of an eye diagram that you would typically see on high-speed oscilloscope. But every clock cycle, there are 4 possible levels that you can or that the signal can be at, and you're going to encode 2 bits of information, 0, 0, 0, 1, 1, 1, or 1, 0. The reason those kind of go out of order, if you're familiar with binary, is that we only want 1 bit to change for each level to try to minimize errors. But one of the things that happens with PAM4 is you're going to get a higher error rate than what was the transmission for 100 gig, just because you can see there's a lot less gap, or they call it I, between these levels than there was before. So that'll bring me to the next topic of forward error correction. But again, I just want to emphasize here the way that we get from 100 gig to 400 gig is we took 100 gig, we added a second row of pins in a QSFP, or changed the optical form factor to OSFP in order to get that second one doubling of density, and then we used PAM4 to send 2 bits of information to get that second times 2. And that's how we get from 100 gig to 400. So I mentioned PAM4 as a new technology in order to get double the bit rate per clock cycle. And I kind of just alluded to this, but this is kind of the challenge is we've got double the clock frequency, but we're much more sensitive to any kind of noise. And there's going to typically in any equipment, there's going to be some level of noise. Again, you've got the 4 levels, so it's not just zeros and ones. It's 2 bits of information that are getting encoded, and you're much more likely to see an error with a PAM4 signal than you are with a what they call NRZ, which is the previous version which was what was used at 100 gig. Now, the good thing is that we have a technology that can anticipate and fix errors. That's called forward error correction. So at 400 gig, all of the different line rates are going to use forward error, or all of the different optical interfaces are going to use forward error correction. Unlike at 100 gig or some of the other rates, sometimes FEC was optional. In this case, it's mandatory in all cases. And the main point of FEC is to anticipate, detect, and then correct errors. And what we're going to be doing is taking each of the bytes of information that is going to be transmitted on the network. We're going to break it up into a group of 544 symbols, and then we're going to encode a message, some additional information about that information that we can then use to fix any errors that crop up and in the course of transmission. And so with the FEC that is being used at 400 gig, you can have up to 15 symbols in error, or 15 symbols with an error, and then you can correct those frames. If you have 16 symbols in error, you're going to have what we consider an uncorrectable error. So one of the things that we're going to start doing at FEC, with FEC at 400 gig is number one, looking at the overall bit error rate that the FEC is correcting. The IEEE recommends that you kind of look at 2.4 times 10 to the minus 4th as the threshold. If you've got better bit error rate than that, then that looks good. That's kind of your your overall maybe pass fail that you would use. Although some organizations may go for a stricter bit error rate, and that's certainly something that could be done. But in general, there's the kind of your overall pass fail is going to be that net bit error rate that you're going to see. So again, 2.4 times 10 to the minus fourth is what the IEEE kind of suggests. But what's also important to look at is what we call the error distribution. That's the table at the bottom right of this screen. What I'm showing you here is what bad looks like. And what you're seeing is, if you remember from the previous slide, and I've got it summarized here as well, we can have up to 15 symbols in error in any one block of 5,440 bits. That can be in error. So a symbol is 10 bits of those information. You can have up to 15, and you can correct it. But the thing is that the number of symbols that are going to be in error is always sort of fluctuating. There's some randomness to it. So if we've got a scenario with lots of, and by lots I mean even a few, with 11, 12, 13, 14, or 15 symbols in error, it's not going to take much, or there's a good chance that we could tip into 16 symbols in error. And in that case, the FEC is not going to be able to work it. And what you're going to see is that the error will show up in your Ethernet signal. That'll show up as it'll be counted as an uncorrectable FEC error. But also the Ethernet frame is going to have an error, and it's going to get dropped. So that's typically the thing that you're trying to avoid in transport networks. So again, exactly where your cutoff here is going to be, well, it may vary by the application, but we generally are suggesting that 10 or fewer symbols in error gives you some level of margin. If you start to see 11, 12, 13, 14, or 15 symbols in error, if you start to see this distribution kind of drip down into this area, that's what we're trying to guard against. If we've got all 1, 2, 3, 4, maybe 5 symbols in error, then we feel like we have a lot of margin. So this is going to be one of the ways that you can identify the amount of margin that you have, both with an individual optic as well as your overall transmission. So I've just got a slide here that talks about some of the different optics that are available for 400 gig. In bold is the 400 gig FR4. The way that you can, this is the most common optic that's available, but what we're really doing is defining all of the different optics by the reach. That's the main thing that's driving. That's that second column. There are versions of these optics that are only 100 meters in length. These are generally the less expensive. FR4 is what a lot of operators will use within the network. That gives you 2 kilometers of distance that are out there. There's also an LR4 as well that'll give you 10 kilometers, and then I'll talk about this in more detail in a few moments, but then there's the ZR Plus that'll give you greater than 40 kilometers up to 80 kilometers in distance, which is kind of a new topic that's coming out. But again, what most people use and that we've seen is FR4. What that uses is it's a single mode fiber with LC connectors, 4 lambdas in each direction, kind of just like at 10 gig, or sorry, 100 gig, there were 4 lambdas in each direction. It's just that in this case, these are going to be running PAM4 as the interface, and then there's the FEC that's there as well. So that gives you kind of a sense of just the different flavors that are available. There are a lot, but generally we're seeing people use FR4, LR4, and some people use the SR 4.2. DR4 is another one that's to some extent becoming popular, and there are several reaches of that from between 500 and 10 kilometers, and these are all MPO connectors. So if you're dealing with that in your application, this is an area where we're dealing with MPO as the connector type. Again, I kind of mentioned just all of the different pluggable optics that are out there, both from SFP, from QSFP. These are some of the different form factors that are available. The new ones that are available for 400 gig is this SFP 56DD. Although there's also an SFP 56 that covers 200 gig, and then I think most people are probably familiar with QSFP 28. In addition to optics, we're seeing a lot of folks use AOC or DAC cables. There are a few other flavors as well for interconnecting within a building. Could be within a data center, could be inside a CO. In these cases, these cables will they have, there's a module on both ends of the cable. And so one of the things that sometimes happens is we might wonder whether or not these cables are going to work or not. That's going to bring me to my next slide of kind of ways that we can prove out whether the new optics that are coming available or the AOC DAC cables are working the way that you're expecting. One of the things that we recommend is to test the pluggables sort of independently of your overall network. So one of the test applications that we've been working with several customers on is just what we call either an optic self-test or a cable test. What this will do is either take a single optic and use a fiber jumper to loop it back. And run a test between just from transmit to receive of the optic and prove out that the optic works the way that we're expecting. The other scenario is if we have a cable and we have modules on both ends. Well, the nice thing is we have capabilities for two ports on a lot of our equipment. So you can put the cable or the optic or the cable in one module on port one module on port two, and then run a test between the two ports. That'll then prove out that the cable is working properly. Again, the idea here is just to segment the problem or just prove to ourselves that the optics or cables work the way that we're expecting them to work. Again, with the sort of higher rates and the PAM4, that's a scenario where it's nice to be able to segment out the problem. We've seen a variety of customers that might see elevated FEC errors, or they might see scenarios where the error distribution in the end-to-end network doesn't look as good, or they don't have as much margin as they would like. So now with these kinds of test methodologies, we can start to segment that problem out. So now I just want to talk about, okay, how do we test? So if we're going to talk first about just testing the optics and cables, that's one thing. How are we going to test end to end? And so I've got this drawing that sort of shows what a typical application would look like with transponders connected to routers and switches across DWDM line system. That's a typical application for 400 gig. So you've got just from left to right a 400 gig router or switch, which a lot of organizations are upgrading to right now. Talking to a transponder here, that's going to be a connection from one of those client optical interfaces. Could be, in many cases, it's going to be FR4 here, to then talking on a coherent interface across the DWDM line system, typically going to be using some flavor of DWDM network. Oftentimes in service provider networks that could be using ROADMs, which is what I've got shown here, across the network, and then connected to transponders and routers in the far end. So this is a typical setup, or a couple typical setups that we could use. What a lot of people like to do when they are testing just the transport portion of the network is they'll hook up on this 400 gig client interface that I talked about a moment ago, and run a test from sort of the left-hand side of the network through the transponder all the way across the transport network to a fiber jumper to a loopback. This is something that you can do just with one unit on one end of the network. loop the traffic back, and then test for your end-to-end bit error rate. So the FEC will typically only exist for each individual portion of the network. The transponder will apply its own FEC, so you'll see both the connection, the forward error correction, and how much it's correcting in your local link. But then we'll also see an overall bit error rate or frame loss rate across the entire network. Really, we're trying to always drive that down as low as possible, but typically zero or very low. But it depends on how long you want to test as to how much confidence you have that it's going to be better than a particular bit error rate. But generally, that's what we're looking for, is error-free transmission across transport networks like this. That's sort of one way that you could actually run the test. The other option that I've got drawn out here is showing testing actually through the router. In this case, you would need to use layer 3 traffic, because routers are layer 3 devices. And in that case, we would probably want to loop back either with another device from the far end, or some routers are able to actually do a layer 3 loop back to swap the transmit and destination IP addresses. So again, that's something that can be done there. So again, from an overall network testing topology, this is not super different than what we did at 100 gig, but it is it's kind of using 400 gig, and then again, each of these individual interfaces, you're going to want to be cognizant of that you've got a sufficient margin in terms of the forward error correction. So that brings me to the end of just what's new at 400 gig. But in addition, and I mentioned this in the different types of optical interfaces, one of the really new technologies that is coming into a lot of networks, a lot of operators are adopting it. A lot of data center operators have been using it for several years, or what's called coherent pluggable optics. So I'll explain what those are and give you some thoughts on how to test them. So the traditional model, and this is very similar to the slide I just showed here. I've got the traditional model and sort of the new model. In the traditional model, we would have had a router or switch connected to a transponder with what we would consider gray optics oftentimes, or those an example would be an FR4 optic. But any of the examples that I showed in the previous previous slide would be able to work. You're typically looking to have the same optical interface on both ends of the link. But these are all going to be these connections here. The gray optical connection is just typically point to point, and you can only have one 400 gig interface on any one particular pair of fibers. But then on the line side of the transponder, and I've got this colored in the red color here, what we're typically going to be doing there is we're going to connect from a transponder into our line system. The transponder is going to it's going to use a coherent modulation. So instead of kind of 4 optical interfaces or four lambdas on the gray optics, this is going to be a single coherent modulated signal that's going to kind of spread out over the course of whatever modulation you're using over the course of some optical bandwidth, and then it's going to be tuned to a particular center frequency that's typically going to be in the C band, although some people are starting to move into the L band as well. So that's that optical line interface that typically came out of a transponder. In the new model, what we're seeing is that you can actually take, for many applications, and again, this is not all applications, but many applications, you can take the technology that was in the transponder and put it into a single optical module. So now the interface that you plug into the router, or the optic that you're going to plug into the router, has not only the ability to send out a coherent modulated signal, but it's also going to be tunable to a particular frequency. And then you're going to connect that directly into the line system. So the advantages to this are that you get to save the capital cost and potentially the sort of operational costs on the transponder, because the pluggable coherent optic is typically, maybe an order of magnitude less expensive than a traditional blade on a transponder. But it's going to allow that to work fairly well for many applications. So you get both a capital savings as well as potentially operational savings from not having to power and take up space within field locations. So that's why people are moving to it. There are some operational implications, though. So one of the thought processes that folks are using is that they want to be able to deploy more coherent interfaces within their network. So that's going to drive a lot more links that are potentially using coherent. If the cost goes down, the number goes up. But one of the things that people tend to want to do with these optics is reuse the existing fiber routes in the existing line system. I know a lot of folks may be involved in creating or constructing fiber or deploying line systems. Typically, you're not going to want to deploy a brand new fiber plant for just using these ZR plus optics. We want to be able to leverage the tools that we already have in place, or the assets that we already have in place. But the other thing that's happening is that we're potentially going to be expanding coherent towards the edge of the network, moving it into locations that maybe I couldn't afford or justify to put an entire transponder into, but we can afford and justify to put a coherent pluggable optic in. Another kind of operational impact is in organization. The organizational demarcation points will change within the network. What used to be a gray optical interface between the router and the transponder is now inside the optic. So you'll need to change where those demarcation points occur within the network. And then you'll have a variety of additional personnel that are involved in activation and troubleshooting. Sometimes in a lot of operators, the transport team may be specialized, a specialized team. In cases where we're converging towards having a single sort of IP team that also does transport, we may have some additional folks that are involved. So how do we test and troubleshoot this? Number one, coherent pluggables and 400 gig in general and coherent pluggables in particular are going to place a lot more emphasis on fiber characterization. I've got the list of different fiber characterization tests that people will many organizations will choose to adopt. Everything starts with making sure that the end faces of fibers are clean. So we should, number one, always inspect inspect the connectors or inspect and clean the connectors before we connect. But then you've got kind of like I like to think of this as like two layers of tests that we run for characterizing fiber that's in the ground. And again, we're probably doing a lot of this stuff when we're constructing fiber, but we may want to go back and double check this if we didn't do this for fiber that's already in service. What I tend to find is that a lot of people will do the top row, the insertion loss and OTDR and optical return loss. And at 100 gig, that was probably good enough. Oftentimes what we would see is that because 100 gig was the first interface that moved to using coherent modulation, it had significantly more tolerance to dispersion than what we had prior to that. With 400 gig and pluggable coherence as a general trend within the industry, we're starting to see a lot tighter dispersion parameters or dispersion requirements. Two different kinds of dispersion: the chromatic dispersion, polarization mode dispersion. That will often dictate whether or not we're going to be able to get high performance or high quality performance across the network. Typically, the optical modules will have their own dispersion criteria, and you'll need to make sure that that the fiber plant that we're traversing is going to be consistent with high quality performance with those optics. So starting to see a lot more emphasis on fiber characterization, in particular the dispersion, as we move into deploying more pluggable coherence. So I showed this slide before. This is kind of our slide of how do we test traditional networks. And I mentioned now, not only are we losing this demarcation point within the organization as we're moving to the transponder network, sorry, moving from transponders to using pluggable coherence, but we're also removing this whole piece of equipment altogether. So what the model would look like with pluggable coherence is that we'll have, I've got the ZR plus pluggable coherent optic kind of colored red here. So we're going to have an optic that gets plugged directly into a router or a switch, and then that's going to have a direct connection into the line system. And I've got that just labeled here, sort of a ROADM, but it's typically a ROADM plus a line system that gets combined into a shelf. And then you're going to transport that across the network. So that's kind of the operational setup. When we're looking at testing, a lot of times what happens is we may want to ask ourselves the questions: what is the performance going to be across the particular optical equipment, the line system, the ROADMs, the fiber that's in the path, from end to end. So sort of one way to do that is just plug the optics into the router or switch and test it that way. That will potentially tie up the port on the router or switch that you're using. And also, if you're using that router for production on other ports, you may want to be able to test independently, or you may not even have the router installed if you're looking at doing an upgrade from an existing 100 gig router to a 400 gig router. You may not have the equipment even on site. So one of the things that you can do instead, if you want to prove that the overall path from one side of the network to the other side is consistent with high quality performance, is we can take a pluggable coherent, put it directly into our test equipment, and connect that into the router or switch. We can run that all the way end to end through the network. One thing to note here is that in this case, where I've got the two units, both with the red symbol for a pluggable coherent optic inserted into them, you're going to need an optic on both ends of the network. Typically, you're not going to be able to just with a reach or the overall dispersion make it end to end through the network without regenerating on the far side. So typically, if you don't have routers on both ends of the network, and you want to do this test, one of the things that we see a lot of folks do is they'll take pluggable coherent into a piece of equipment, a test set on one side, pluggable coherent into a test set on the other side, and you'll run that test end to end through the network to prove high quality performance. So I look at it as sort of a three-stage step here. I've got at the top, this is kind of the same topology. I just sort of flattened it a little bit. And number one is just like I pointed out at the beginning. Take the optic, put it into the test set, ensure that it works by itself, just in a self loop, without having any problems. Again, these optics are generally going to be several $1,000s in cost, so you want to just prove out that the optic works and is going to work well before you're going to actually use it within the network. So then you can, number one, set up the optic and configure it. There are some configuration parameters that you may need to tweak here in order to get high quality performance through the particular kind of network that you've got. There are typically some presets that the vendors use, and that's something that we would need to qualify before deployment. But we can also then tune to the correct wavelength, set the appropriate power level, and then prove that we're getting acceptable FEC, error correction, and 0-bit error in soft loop. Step 2 would be to run an end-to-end Ethernet test. In this case, what we would be looking for is typically 0 packet loss. That's typically what we would do, as I mentioned earlier, in an overall transport testing use case. But what's a little bit new with the coherent pluggables is that the optics will also report what we call the coherent statistics. So this will be things like the prefect bit error rate on the optics. So again, there's an end-to-end FEC. That's getting applied. But also sort of what it sees in the optical domain as it's trying to demodulate the signal. So it could be it's going to measure things like OSNR or differential group delay. These are sort of the optical parameters that typically have been reported from a transponder. In this case, they're also going to be reported from these coherent pluggable optics. And again, that's going to the 0-bit error rate is kind of like what we're overall looking for, but we're also going to want to monitor those coherent statistics to see how much margin do we have in the network all together. And then finally, we're going to want to do optical spectrum analysis. This could be a troubleshooting step, or it could also just give us a sense of how much margin we have overall in the network. In a lot of cases, these pluggable coherents, when they're plugging into a line system with other transponders or other transponders going through a ROADM network, you refer to the coherent pluggables as an alien wave. And so you may need to double check how the other network or other traffic or other wavelengths in the network is interacting with our particular signal, or making sure that our signal is not interfering with other signals, other production signals. And we can do that via optical spectrum analysis. And he also it gives us another mechanism for getting a sense of OSNR optically. So if we're seeing OSNR from the optic, we can try to figure out where is it coming from, what could be causing the problem. And then lastly, we can repeat these steps in the reverse direction. So again, it's going to be a two-sided test. We could be doing it with a loop back, and that's typically how people would do it. But we do probably want to measure things like our coherent statistics in the direction from A to Z, and then also in the direction from Z to A. And so one of the things that we can do here, and again, this is just a sort of a visualization of the two sort of steps 2 and steps 3, is running 400 gig of traffic through a coherent pluggable. That's the screen on the left, and then the screen on the right is showing optical spectrum analysis. And I've just zoomed in here. I've got just one channel on this particular network, but it's kind of zoomed in on one particular channel, and you can toggle between those two. So that's kind of the overall on coherent pluggables. Again, it's something that we're seeing happen or being deployed increasingly. Actually, the last thing I will note, just on the coherent pluggables, that they came out first at 400 gig. But we're also seeing people deploy 100 gig coherent pluggables as well. These are optics that are actually in a QSFP28 form factor. So again, the coherent pluggable doesn't necessarily mean only 400 gig, because it could be also 100 gig. And as I'll mention in just a moment, it's also going to be pretty important for 800 gig. So let's talk about just some of the overall market trends that we're starting to see for 800 gig deployment. This is a relatively new technology that has been used in data centers for maybe the last 18 months or so. They use a variety of 800 gig optics and cables. They could be in many cases, it's not necessarily 800 gig E, but it's a breakout variant. So it could be 2x400 or 8x100. Again, those are kind of used in data centers, especially AI data centers now. But we're also seeing 800 gig data center interconnect, and DCI stands for data center interconnect, applications getting ready for field deployment in the first half of 2025. Seeing a lot of sort of early field tests that we're involved in. And we're starting to see a lot of operators start to prove out 800 gig in their labs. The other thing that's sort of just around the corner is pluggable coherent optics, which we are starting to see generally available in the first half of 2025. That's one of the things that's a little different than 400 gig, where the pluggable coherence lagged by a couple of years. The transponders, in this case, they're both coming out at the same time. So both the applications that I talked about for 400 gig, whether it's a traditional deployment or a coherent pluggable deployment, may be happening pretty soon for 800 gig. The other thing that we're happening, and I mentioned this kind of right at the start of the presentation, is we had new form factors of optics at 400 gig. Now, there were two different form factors that were defined, but most people at 400 gig use QSFP. It's a little smaller. You can get more density in the equipment. I think a lot of folks just like being able to stick with QSFP just as a general form factor. At 800 gig, we're starting to see a bigger mix of QSFP and OSFP, and in particular in the pluggable coherence. We're seeing a lot more OSFP than we did with 400 gig. So the OSFP form factor, we'll see how far it breaks out of the data center into operators or service providers, but we're definitely seeing it a lot more at 800 gig than we did at 400 gig. And then we're also seeing within data centers, especially AI data centers, we're seeing a lot more AOC DAC cables than we ever did. So let's, how do we get, again, this is the kind of a repeat of the slide that I had, or the new version of the slide that I had before, just to try to make this simple. So we knew how we got from 100 gig to 400 gig. From 400 gig to 800 gig, what we're really doing is doubling the speed on the electrical interface from the optics into the equipment. So we're using the same 8 lanes that we had before. So these are still QSFP, DD, and the OSFP. They still have the same 8 lanes. So that's exactly the same. What we're doing is we're running them at twice the clock speed. So for 800 gig, it'd be 106 gigabits per second per lane, 8 of those, instead of 53 gigabits per second at 400 gig. And then the optics have sort of new names, QSFP DD 800 and OSFP 800 to differentiate from the versions that were available at 400 gig. So the main thing here is that we are doubling the density of the optics, or sorry, doubling the clock speed of the optics. Logically, there's a little bit of a difference as well, in that, or actually it's a lot of bit of a difference, but this is one of the ways that the way that you get to achieve 800 gig E in sort of the logic of the equipment, is that we're doubling the data rate and we're adding what's effectively a second 400 gig flow in the PCS layer of the optics. So the way that we're talked about all our FEC at 400 gig, we're using that same FEC that we used before. It's the exact same FEC that we used at 400 gig. We just have 2 of them. So at 800 gig, we have a flow 0 and a flow 1. They each have their own FEC. I kind of got that labeled here in the diagram to the right, where you see both of those two flows, and both of them have effect in the transmit and then in the receive direction. So that's kind of, there's a little bit of a complication there. There's more information because we're doubling the data rate, doubling the number of FECs. I think the good news is that if we stay focused on the error distribution table, this is really still the most important indicator of how much margin you have on with whether it's the optic in a self-loop scenario, an AOC cable or DAC cable that you're connecting equipment between, or even just a transmission through the network. The error distribution table is still the main thing that we want to focus on. Again, we're doubling the speed, doubling the number of FECs, but that error distribution table is still the most important indicator that's out there. In terms of applications and optics, at 800 gig, I think one of the things that we're seeing, I've got sort of labeled here, 2x400 gig and 800 gig optics. These are kind of like a top view of the optic if you were looking down on it. On the left-hand column here is a 2x400 gig, which is still it's 800. It's a 800 gig total capacity optic, but that has two 400 gig E interfaces that are operational on it. The right-hand column is 800 gig E, so a single logical 800 gig E flow that is able to use a single 800 gig optic. You can see some of the popular ones. There's a lot of, we see 2x FR4. FR4 again, that's on the left-hand column. Those are 400 gig optical interfaces. So it's a 2x FR4 optical interface, and you've got actually two different pairs of LCs, kind of one on the left and one on the right. So it can be a little tough to cable up if and get in there, but that's one of the interfaces there. You've also got capabilities for MPO interfaces there, or two MPO12s. And then on the right-hand column, you've got the ZR that's on the top. There was a standard for FR8 that's not super widely deployed currently. I think a lot of people in FR are going to wait for sort of a next generation optic that's going to be FR4. Those typically aren't available yet, but ZR will be available relatively soon, so it's kind of an interesting one. But then I think one of the most popular for 800 gig E right now is the DR8. This is using an MPO16 connector, and that's going to be it's probably the most popular interface that's available right now. It does use MPO though, so that's one of the potential drawbacks, is because you're just dealing with MPO interfaces in general. MPO and MPO16 in particular can be a challenge sometimes. So now, I'm happy to just share. This is a brand new product for us. It's in our OneAdvisor 800. It's 800 gig transport module. We are going to be formally announcing it in a press release that comes out tomorrow, but you guys are all going to get a preview of this today. I think one of the great things about this particular module is that it's going to have two QSFP DD800 interfaces, two OSFP interfaces. So you can do AOC DAC tests with a single unit, and you don't need to pick between OSFP or QSFP up front, because the equipment can support both. We will have extensive support for the Coherent pluggables, both for 800 gig, as well as the lower rates of the 400 gig and 100 gig, and even all the way down to 10 meg. All the tests that I talked about, and the sort of the optical interface is the same as what we've done before, 400 gig all the way down to 10 gig for folks that have been around with us for a while. And then within the ONA 800, we've got a variety of different test applications for fiber optic testing, whether it's VFL or broadband power meter, testing fiber optics with OTDRs for troubleshooting, OSA for DWDM analysis, and then a power expansion module for extra battery. So a variety of things there that a lot of folks can take advantage of. Lastly, I just want to round out the presentation by covering off just a variety of the different equipment that you want to consider if you're looking at adopting 400 gig or 800 gig technology. I mentioned the 800 gig transport module. We have a 400 gig transport module that a lot of folks have adopted. In the middle of the screen is the INX. This is our scope for it can do duplex LC testing. It can do MPO testing with a single button push. If you're going to be moving into any of these higher density type applications, we using whether it's MPO or whether it's duplex LC or 2 duplex LCs, there's a lot more fiber to inspect. And this guy will do everything everything you need really easily. And then on the right hand side, I've got a couple of configurations lined out. The bottom one kind of just shows our existing 400 gig transport module, OTDR and an OSA. And the top module there also shows how we can do dispersion testing and bidirectional OTDR. So all of the tests that I introduced over the course of this presentation kind of can be done with a single unit, and there's nothing to change around or need to reconnect. So with that, I will kind of wrap up our presentation. Just give another plug for OFC, which is in San Francisco this year. If you're going to be in the San Francisco area or you're going to be coming to OFC in particular, we'd certainly love to show some of this equipment to you. We'll be at booth 2319. That's the week of April 1st through 3rd. And if you have any questions, looks like we have about 8 minutes. So happy to try to address questions if there are any.
So we had a few that I was able to answer in line, and
Okay.
we don't have any new ones at this moment.
Okay. Well, we'll give folks a minute to ask any questions. If not, then I certainly thanks to everybody for your attention.
Okay. Thank you, everyone, for attending the webinar. As stated, the recording will be available. We're going to try and have it before March 14th conclusion of that webinar, but in any case, you will receive a link to get the recording shortly. We got a great presentation, a couple of those, Michael, so thank you so much, and thanks everyone for attending. We'll conclude the webinar now. We have one question. Will there be a webinar focused more to installation, INR? LNR?
Yeah, INR is installation and repair. I'd certainly be happy to. We could certainly do something like that if you want to email us with particular topics that you'd like to cover, or maybe some more details. We often do. This was kind of just a high level, presentation of some of the new changes. I know a lot of folks oftentimes also would like to see some hands-on live demonstration type stuff. If that's what you're interested in, I know one of my colleagues typically monthly does that, so we can get you.
Oh, that'd be great.
Get you invited to that.
Okay. All right. Well, thank you, everyone. With this, we will conclude the webinar. Thank you.